Good afternoon, Professor and everyone. Today, our group will present the Knowledge Graph, Chapter 4, Deductive Knowledge. There are two main sections in this chapter, which are the ontologies and reasoning. We divided into three parts, and I'm going to present the first parts of this chapter, which are the interpretations and models and the ontology features. Let's start with the introduction. As humans, we can deduce more from the data graph of figure 2.1 than what the ages explicitly indicate. For example, the NAMM Festival will be located in San Diego, right? Even though the graph doesn't contain an age location. We may further deduce that the city connected by flights must have some airport nearby, even though the graph doesn't contain nodes referring to this airport. And in this case, given the data as premises and some general rules about the world that we may know a priori, we can use a deductive process to derive new data, allowing us to know more than what is explicitly given by the data. These types of general premises and rules, when shared by many people, form part of common sense knowledge. When rather shared by a few experts in an area, they form part of domain knowledge. For example, an expert in biology may know that hemocyanide is a protein containing copper that carries oxygen in the blood of some species of mollusca and arthropoda. In contrast, machines don't have a priori access to such deductive faculties. They need to be given formal instruction in terms of premises and entailment regimes. In this way, we will be making more of the meaning of the graph explicit in a machine-readable format. These entailment regimes formalize the conclusions that logically follow as a consequence of a given set of premises. Once instructed in this manner, machines can apply deductions with a precision, efficiency, and scale beyond human performance. These deductions may serve a range of applications, such as improving query answering, classification, or finding inconsistencies. As a concrete example involving query answering, assume we are interested in knowing the festival located in San Diego. We may straightforwardly express such a query as per the graph pattern shown in Figure 4.1. But this query returns no result for the graph in Figure 2.1. Let me turn back to this figure. There is no node named Festival, right? And nothing has directly the location to San Diego. However, an answer, NAMM, could be automatically entailed where we just state that X being a food festival entails that X is a festival, or that X having venue Y in the city C entails that X had location C. In this chapter, we discuss ways in which more complex entailments can be expressed and automated. We focus on ontologies, which constitute formal representation of knowledge that, importantly for us, can be represented as a graph. We discuss how these ontologies can be formally defined, how they relate to existing logical frameworks, and how reasoning can be conducted with respect to such ontologies. I will walk you through the first section of this chapter, ontologies. To enable entailment, we must be precise about what the terms we use mean. Returning to Figure 2.1 again, for example, if we examine the node EID16 more closely, we may begin to question how it is modeled, particularly in comparison with EID15. And according to the class hierarchy of Figure 3.1, they both consider to be events. But what if we wish to define two pairs of start and end dates for EID16 corresponding to the different venues? Should we rather consider what takes place in each venue as a different event? Or would this also be considered as one event or many events? These questions are facets of a more general question. What precisely do we mean by an event? Does it happen in one contiguous time interval, or can it happen many times? Does it happen in one place, or can it happen in multiple? There are no correct answers to such questions. We may understand the term event in a variety of ways, and thus the answers are a matter of convention. In the context of computing, an ontology is a concrete, formal representation of what terms mean within the scope in which they are used. For example, one event ontology may formally define that if an entity is an event, then it has precisely one venue and precisely one time instant in which it begins. Conversely, a different event ontology may define that an event can have multiple venues and multiple start times. Each such ontology formally captures a particular perspective or a particular convention. For example, under the first ontology, we couldn't call the Olympics an event, while under the second ontology, we could. Likewise, ontologies can guide how graph data are modeled. Under the first ontology, we may split EID16 into two events. Under the second, we may elect to keep EID16 as one event with two venues. Ultimately, given that ontologies are formal representations, they can be used to automate entitlement. Like all conventions, the usefulness of an ontology depends on the level of agreement on what that ontology defines, how detailed it is, and how broadly and consistently it is adopted. Agreement over multiple knowledge graphs will in turn enhance the interoperability of those knowledge graphs. Among the most popular ontology languages used in practice are the web ontology language, recommended by the W3C and compatible with RDF graphs, and the open biomedical ontologies format, used mostly in the biomedical domain. Since web ontology language is the more widely adopted, we focus on its features, though many similar features are found in both. Before introducing such features, however, we must discuss how graphs are to be interpreted. Let's talk about interpretations and models. As humans, we may interpret the node San Diego as referring to the real-world city that is the capital of Chile. We may further interpret an age flight as stating that there are flights from the city of Arica to the city San Diego. We thus interpret the data graph as another graph. What we here call is the domain graph. The domain graph composed of real-world entities connected by real-world relations. The process of interpretation involves mapping the nodes and edges in the data graph to nodes and edges of the domain graph. We can abstractly define an interpretation of a data graph as being composed of two elements, which are a domain graph and a mapping. The domain graph follows the same model as the data graph. For example, if the data graph is a directed edge-level graph, then it will be the domain graph too. For simplicity, we will speak of directed edge-level graphs and refer to the nodes of the domain graph as entities and to its edges as relations. Given a data graph and an interpretation, while we denote nodes in the data graph by this pattern, we will denote the entity it refers to in the domain graph by this pattern, per the mapping of the given interpretation. Likewise, while we denote an edge by this pattern, we will denote the relation by this pattern. In this abstract notion of an interpretation, we don't require that the San Diego or Arica be the real-world cities, nor even that the domain graph contain real-world entities and relations. An interpretation can have any domain graph and mapping. And why is such an abstract notion of interpretation useful? The distinction between nodes or edges and entities or relations becomes important when we define the meaning of ontology features and entailment. To illustrate this distinction, if we ask is there an edge-level flight between Arica and Vinodemar, the answer is no. But if we ask if the entities Erika and Winodemar are connected by the relation flight? The answer depends on what assumptions we make when interpreting the graph. Under the closed world assumption, if we don't have additional knowledge, then the answer is the definite no, since what is not known is assumed to be false. Conversely, under the open world assumption, we cannot be certain that this relation doesn't exist, as this could be part of some knowledge not yet described by the graph. Likewise, under the unique name assumption, the data graph describes at least 2 flights to San Diego, since Winodemar and Erika are assumed to be different entities. Therefore, Erika flies San Diego and Winodemar flies San Diego must be different agents. Conversely, under no unique name assumption, we can only say that there is at least one such flight, since Winodemar and Erika may be the same entity with 2 names. These assumptions define which interpretations are valid and which interpretations satisfy which data graphs. A graph interpretation captures the assumptions under which the semantic of a graph can be defined. We define interpretations for directed age-level graphs, though the notion extends naturally to other graph models, assuming the data and domain graph follow the same model. The definition of graph interpretation: a graph interpretation I is defined as a pair I equal to gamma and this symbol. I'm sorry, I'm not sure how to read this symbol. And gamma is a directed age-level graph called the domain graph, and this symbol is a partial mapping from constant to terms in the domain graph. We denote the domain of the mapping by this symbol. For interpretation, under the unique name assumption, the mapping is required to be injective, while with no unique name assumption, no such requirement is necessary. Interpretations that satisfy a graph are then said to be models of that graph. The definition of graph model: let G be a directed age-level graph and interpretation I satisfies G if and only if the following hold. And next, I will show you about the ontology features. The first feature is individuals. In Table 4.1, we list the main features supported by OWL for describing individuals. Sometimes distinguished from classes and properties. First, we can assert relations between individuals using ages, such as Chile, capital, San Diego. In the condition column, when we write this pattern, for example, we refer to the condition that the relation is given in the domain graph of the interpretation. If so, the interpretation satisfies the axiom. And OWL further allows for defining relations to explicitly state that 2 terms refer to the same entity. For example, like this, state that both refer to the same region, or that 2 terms refer to the different entity, like this example. It distinguishes the city from the region of the same name. And we may also state that a relation doesn't hold using negation, which can be serialized as a graph using a form of reification. Next feature is properties. From the chapter 3, we already discussed how subproperty, domain, and range may be defined for properties. And OWL allows such definition and further includes other features as listed in this table 4.2. We may define a pair of properties to be equivalent, inverse, or disjoint. We may define a pair of properties to be equivalent, inverse, or disjoint. And we can further define a particular property to denote a transitive, symmetric, asymmetric, reflexive, or irreflexive relation. We can also define the multiplicity of the relation denoted by properties based on being functional, many to one, or inverse functional one-to-many. We may further define a key for a class, denoting the set of properties whose value uniquely identify the entities of that class. Without adopting a unique name assumption from these latter three features, we may conclude that two or more terms refer to the same entity. Finally, we can relate a property to a chain, such that pair of entities related by the chain are also related by the given property. Next feature is classes. In the chapter 3, we also discussed how class hierarchies can be modeled using a subclass relation. OWL supports subclasses and many additional features. For defining and making claims about classes, these additional features are summarized in this table. Given a pair of classes, OWL allows for defining that they are equivalent or disjoint. Thereafter, OWL provides a variety of features for defining novel classes by applying set operator on other classes or based on conditions that the properties of its instances satisfy. First, using set operators, one can define a novel class as the complement of another class, the union and intersection of a list of other classes, or as an enumeration of all its instances. Second, by placing restriction on a particular property P, one can define classes whose instances are all of the entities that have some value from a given class on P and all values from a given class on P. Has value means have a specific individual as a value on P. Has self means have themselves as a reflexive value on P. Cardinality means have at least as most or exactly some number of values on P. And the last one, qualified cardinalities, mean have at least as most or exactly some number of values on P from a given class. And now is the end of my part. Thank you for listening.
Next is other features. OWL also supports features not previously discussed. First, as annotation properties, it means metadata about ontology. For example, there is version information data. Second, it is a property that uses data type value as data type properties. Third, it is a property that does not use a data type value as an object properties. Finally, there are data type passes. Data type passes define new data types by applying restrictions to existing data types. For example, a location called Chile could create a new definition that should have a float between minus 66.0 and the minus 110.0 as a value of the data type attribute latitude. Next is models under semantic conditions. The axioms of ontology features described previously apply some conditions to the graph model when they are added to the graph. For example, considering only the condition of the assertion feature in table 4.1, the graph model can interpret that a relation xyz exists for all edges xyz of the graph. Next, considering that multiple nodes in the graph can be mapped to one entity in the graph model, interpretation will map everything to one. For example, interpretation with relation AAA is a graph model in which x equal y equal z equal a is maintained for every edge xyz of the graph. Finally, as we add axioms with their associated conditions to the graph, we restrict models for the graph. For example, considering a graph with two edges x, y, z and the y type, here reflexive the above interpretation using AAA, x equal y equal ellipsis equal a is no longer a graph model. because it breaks the condition of the irreflexive axiom shown in Table 4.2. In this way, we can define precise model theoretic semantics for a graph based on how the previously described ontological features used in the graph constrain the graph model. 2 to the large G represents all directed edge labels, graph set, and semantic condition returns true or false with 2 to the large G as input the mapping pi. It is the mod of G only if the interpretation I is the model of G, pi of gamma. Given a set of semantic conditions pi, we say that I is a model of G if and only if I is a model of G and for all gamma of each semantic condition in the semantic condition set is true. As an example, first order logic, or FOL for short, defines the has value semantic condition in table 4.3 as follows. For all CPY, the semantic condition can be defined such that the preceding and following conditions satisfy if and only if IFF for short. The previous condition is the logical product of the domain graph composed of C I property P and the domain graph composed of C I value Y, and the logical product returns false if both propositions are not true. The latter conditions are domain graphs composed of X I type C for all X and IFF between domain graph composed of XPY. Other semantic conditions listed previously can be defined in a similar manner. Next is entailment. Conditions is previous ontology. Features give rise to entailments. For example, definition nearby type symmetric edge Santiago nearby Santiago Airport entails edge Santiago Airport nearby Santiago according to the symmetric feature of table 4.2. I will explain how conditions lead to entailments. When one graph entails another graph, it means that the formal graph model is also the latter graph model. Intuitively, it means that the latter graph does not represent anything new to the formal graph and thus remains the logical result of the formal graph. For example, when two graph Santiago type city subclass of place, Santiago type place exists, all models in the latter graph must have Santiago type place, and all models in the formal graph must have Santiago type city subclass of place, and Santiago type place to satisfy the subclass condition of table 4.3. Therefore, it can be concluded that all models of the formal graph become models of the latter graph and that the formal graph entails the latter graph. So graph entailment means that if there are two graphs G1, G2, and semantic conditions that pi, G1 entails G2 only when G1 model under pi is G2 model under pi. The expression is as follows. Next is if-then versus if and only if semantics. Considering the two graph nearby type symmetric, nearby inverse of nearby, both graphs have the same semantic conditions applied to the domain graph. But the answer to the question of whether one entails to other depends on the applied semantic system. Considering axioms and conditions, two semantics can be considered. In the first if-then semantics. If axiom matches the data graph, then condition holds in domain graph. The graphs do not intermingle with each other. Both graphs give rise to the same condition, but the condition is not translated into the axiom that describes it. Conversely, in the second if and only if semantics, the axiom matches data graph if and only if condition holds in the domain graph and the graph intermingle with each other. Both graphs generate the same condition and transform it into all possible axioms that describe it. Since if and only if semantics can entail more axioms than if-then semantics in ontology language, OWL applies if and only if semantics to enable richer enumeration. Next is reasoning. With the definition of ontological features and intermingle above give two graphs, it is impossible to determine whether the first graph entails the second graph. There can be no definitive algorithm or interminglers that are interrupted for all inputs, but practical reasoning algorithms for ontology to exist. The first option stops on all input ontology pairs. However, interminglers may be missed and in some cases return false instead of true. The second always breaks with the correct answer. However, it only accepts input ontology with limited features. The third returns correct answer only for its input ontology pairs but does not stop at the specific input. The third option was explored using theorem provers for FOL, but the first and second options are more commonly pursued using rule and description logics. The first option generally allows for inefficient and scalable reasoning algorithm, though it is useful when the data is incomplete and some entailments are needed. The second option is recommended for areas such as medical ontology where missing entailments may lead to undesirable outcomes. Next is rules. A simple way to provide automated access to knowledge that can be deduced through interminglers is to use inference rules that encode if-then style consequences. A rule consists of a body and the head. If is the body and then is the head. The body and the head are provided as graph patterns. According to the rule, if it is possible to replace the variables in the body with the terms of the data graph and form a subgraph of the given data graph, then a valid entailment can be obtained by using the same replacement of variables in the head. The head should use a subset of the variables appearing in the body to ensure that there are no unconcluded variables. Rules can capture entailments under ontological conditions. Table 4.4 lists some example rules. These rules can be considered incomplete. For example, it may not capture that every class is its own subclass and that every attribute is its own sub-attribute. These rules are incomplete because they cannot fully capture negation, existentials, universals, and counting. However, other rules languages have been proposed to support additional features such as existentials and disjunctions. Rules can be used for reasoning in several ways. Materialization is the concept of recursively applying a rule to the graph and adding the generated conclusion back to the graph until a fixed point is reached and no more can be added. A materialized graph can be treated just like any other graph. The efficiency and the scalability of materialization can be improved through optimization or improved by using distributed frameworks. But depending on rules and data, the materialized graph can become too large to manage it. Another strategy is to use rules for query rewriting. Query automatically expands the query to find solution inherent in the rule set. For example, if the schema graph in figure 3.2 and table 4.4 rules are used, the sub-pattern $X type event of a given input query is evaluated in the original graph and then rewritten as the disjunctive parent. Figure 4.2 provides a more complete example of the ontology used to rewrite the query in figure 4.1. The query is to ask what is the name of the festival located in Santiago. When evaluated through the graph in figure 2.1, NAM is returned as a solution. Like this, not all of the OUT figures we saw earlier are supported in this way. The format is the OUT2QL profile, which is a subset of OUT designed specifically for query rewriting. A rule can be used to partially capture ontological entailments, but it can also be defined independently of ontology language by capturing entailments for a given domain. Some rules cannot be captured with previous ontology features because they do not support relational inference method in cyclical graph patterns. As an example, domestic flight cannot be inferred using only flight and country. Various languages can be used to express rules in graph along with independent or ontology languages. An example of a language is notation 3 and 3, rule interchange format RIF, semantic web rule language SWRL, and the Sparkle inferencing notation SPIN.
Hello, my name is Guilherme. Everyone calls me Gin. I will continue the presentation by talking about the rule definitions. A rule is a pair of B and H, such as B and H are graph patterns, and the restrictions that the variables in the head, or H, must be contained in B, the body. So the graph patterns B are called body of the rule, and H are called head of the rule. So as you can see in the table, all variables in the head on the right column are contained in the body, the middle column. The definition of a rule applies for both directed edge-labeled graphs and property graphs. You just need to consider the corresponding type of graph pattern. So if you're using the directed edge-labeled graphs, you have to use its own corresponding graph pattern. So we want to apply, want to make a rule application. Okay, so for a given rule R with body and head, B and H, and graph G, a rule is applied by computing the mapping of the body to the graph and then using those mappings to substitute the variables in H. So as you can see, R over G is the union of those mappings and substitute the variable in H. We can go a bit further as what if we are talking about a set of rules and not only one rule? So given that this curly R is a set of rules containing R1, R2, R3, and multiple rules, like we can then note that the set of rules over G is the union of the application of all rules of the set over G. We can go also further saying that R plus over G is the extension of G with respect of the application of R. As you can see with the R plus would be the RG union G. Finally, we can denote that Rk, k being a positive integer over G, is the recursive application of R plus over G. That means that R1 over G is the same as R plus over G that I just explained. But Ri plus 1G over G would be equal to R plus over Ri over G. So it's a recursive application you can apply and apply, so on. At some point when applying recursively, you will reach that Ri over G will be equal to Ri plus 1 over G. So the rule application will reach a fixed point. And that's when we say that we have achieved the least model. So the least model is defined as R star over G. After defining the least model, we can finally define how to calculate the entailment using rules. Rules can support graph entailments of the form G1 entails G2 under phi, phi being a set of semantic conditions. We can then say that a set of rules R is correct for phi if for any graph G, G entails R star over G under phi. And we can finally say that R is complete for phi if for any graph G, there does not exist a graph G line that is not containing R star over G, such that G entails G line under phi. In other words, if G entails G line under phi, the G line must be also contained in R star over G. Rules can also be directly defined using rule languages such as N3, RIF, SWRL, and SPIN, but those are not further explained in this chapter. If you have any interest, you can enter those links and study further about the rule languages. Now let's talk about description logics. I will introduce a bit. The description logics, or DL, form a family of logics rather than a particular logic. It was first used to formalize the meaning of frame and semantic network, and you might think that it's quite similar to the knowledge graphs, and that's not a coincidence. It have heavily influenced the web ontology language, and thus hold an important place in the logical formalization of the knowledge graph itself. It was first introduced as a restricted fragments of the first order logics that permitted decidable reasoning tasks such as entailment checking, and later were extended with features beyond the first order logic that are useful in the context of modeling graph data such as transitive closure, data types, etc. With the introduction gone, we can talk about the basic elements that compose the description logic. There are three types of elements: the individuals, that we are using the Chile example that we already know. The individuals could be Santiago or Arica. We have classes, here we call it concepts. It can be the city or a place. And we have properties, here called roles, that are the flight or connect to, the relations. The DLs are also composed by axioms. We have the assertional axioms. There are unary class on individuals or binary property relations on individuals. We call the assertional axioms as A-box. as a unary class on individuals could be city Santiago, or as binary property on individuals could be flight Santiago Arica. We also have the class axioms, which are logical operation on classes. It forms the terminology box or T-box. An example would be that cities are subclasses of place. And finally, we have the property axiom, which are logical operations on properties. It forms the rule box or R box, and we can, as example, we use that flights are sub-properties or connect to. Now I will show some examples on how those axioms are used. The DLs have a rich set of logical symbols, and that way we can define new classes based on existing terms. The first example, it shows a class that defines the nearby individuals, the individuals nearby an airport. The second example are all the individuals that have a flight and must be nearby an airport. And the third example is showing that airports are either under domestic airport, international airport, or both. However, uh, even though we have rich logical symbols and many operations, to ensure decidability, we have to restrict the use of some operations. In that example, we say that domestic airports have only one country as destination, but that way we have to use the chain operation, and the chain operation is often not used so to ensure the decidability. So that example is often not supported in most description logics. Now let's go to the definition of DLs. A DL knowledge base K is defined by a tuple ATR, which is the A box, T box, and R box that we already discussed. And about interpretations that were already discussed in this presentation, a DL interpretation I is defined as a pair of domain and functions. The interpretation domain is a set of individuals, and the interpretation functions accept definitions of individual A, class C, and relation R. The individual A would be an element of the domain, the class C would be a subset of the domain, and the relation R would be a set of pairs from the domain. Since it might be hard to understand, I will show an example. Let's say that K is a DL containing the A box, T box, and R box. The A box contains city Arica, city Santiago, and flight Arica Santiago. The T box contains city as a subclass of place, and that all individuals that have a flight have an airport nearby. And as the R box, we have that flight is a sub-property of connects to. And for the DL interpretation containing the interpretation domain and interpretation functions, we have that the interpretation domain contains the port, a mountain, and a plane. The individual Arica I has the element port, that Santiago I has the element mountain, and the individual Arica airport has the element plane. We have that the class city has the subset port mounting, and the class airport has the subset plane. And we have that the relation flight has the pair port mounting, the connects to has the pair port mounting, and the relation cells has the pair plane coffee. As you can see, the DL interpretation I is not a model for K because it does not have the place, the class place, which CT would be a subclass of, and does not have the relation, the class nearby. So it cannot be a model. However, if we introduce those two that were missing, the class place with the subset port mounting and the relation nearby with the pair port airport, we would have it as a model to the DLK. But then how do we define the entailment using description logics? Well, let's use K1, the same as the K from the previous slide, and K2 as description logic only containing connects to Arica Santiago. Well, at first you would say that K1 does not entail K2 because connects to Arica Santiago is not in K1. But the definition says that K1 entails K2 if and only if any model of K1 is a model of K2. Well, any model of K1 would have to have the flight is a sub-property of connects to, and would also have to have the relation the relation flight Arica Santiago. A model that contains those two also contains connects to Arica Santiago. So all models of K1 are also models of K2. So K1 entails K2. On the table on the right, there is a comprehensible list of description logic semantics, but we cannot use all of them. Like I said, we want decidability, and when you use all of those, we cannot have decidability. So we have to make restrictions. And those restrictions, we can apply different types of restrictions, implying different trade-offs. Some restrictions will be faster, but less complex, or some will have more complexity, less restrictions, but they will have more complex computation. Those are the restrictions defined in the book. The ALC, for example, supports atomic classes, the top-bottom classes, class intersection, union, negation, universal restrictions, existential restrictions, and so on. The S extends the ALC with transitive closure. So we have to use either ALC or S. We can also have either H or R. We can have the O, the I, and either F, N, or Q. So we can make a combination of those, but as we add more, it will add complexity and also computation power. So there is different trade-offs for each combination that you use of restrictions. For Y, those are the restrictions, and why we cannot add more or less. It is not detailed in this chapter or in the book, but the author says that if you want to study more about that, it's another field, but I can leave the link later if anyone wants. And that's it for our presentation. Thank you for your attention, and if you have any questions, you can post in the comments.